Baseball players. You guys were here for it. I guess I have to say it again. So anyway, the basic idea is the graph over here on the left is the percentage of actual stolen bases. Very skewed, but for the one on the right, if we take 100 simple random samples, each one size 45, and we look at the mean of each of those 100 samples, we get a much nicer looking distribution, right? There's a lot less variability. It's more symmetric, which of course would lead to less variability. But our centers will be the same. And so that's essentially the gist of this. We're going to look at what happens when we look at sample means in comparison to our actual data for an entire population. All right. So we're going to do a problem. Here we go. And I actually have to first introduce a part. All right. So if x bar is the mean of a sampling distribution of an SRS, a simple random sample size n All right, so the mean of the sampling distribution not a huge change from what we're talking about population proportions as well, right? Yeah, the mean of the sampling, so the mean of the sampling distribution of the means of all the samples, you know what I'm saying? So you grab a bunch of samples, and like in the last case, we took 100 of size 45, and we calculated the mean of each of those 100 samples. It turns out that if you do that, the mean of those means should be the same as the mean of the population. Yeah? This guy here is a statistic. That one's a parameter. Okay? I mean, and it makes sense if you think about it. It would be weird if it was different, right? If you grabbed, like if you had a population and you knew the actual mean value for the whole population, and then you took a bunch of samples from that population randomly, if you take enough, it makes sense that the mean of those samples should be the same as the mean of the population. You know what I'm saying? It makes sense. It would be weird if it was different. Okay. And then, additionally, the standard deviation. And in order to use this, you have to check the 10% condition. Okay. So there we go. And that all makes sense. All right. Also, it's the case, guys, that if you are, well, we'll talk about normal population here in a bit. Let's do it. Come on. There we go. All right. So, we've got the number of movies viewed. In the last year by high school students, we had an average of 19.3 with a standard deviation of 15.8. We took a simple random sample of 100 high school students, and we calculated the mean number of movies viewed by members in the sample. We want to know what is the mean of the sampling distribution of X bar. So our sampling distribution is going to be the same as that of the population, right? So the mean of the sampling distribution should be the same as that of the mean of X bar, of the population. Okay.
Was it recording
Nope. Hey, standard deviation of the sampling distribution. First of all, we have to check the 10% rule. So in the case that not equal, sorry, is greater than or equal to . And what do we got? Let's see. So we're saying that our population should be I think that it would be safe to say that the high school has more than 1,000 students. Huh? Yeah. And I think we're talking about all high school students. So now that I look at it again. So then let's go ahead and calculate sigma sub x bar, the standard deviation of the sample means. In this case, sample mean. And that is sigma divided by square root of n. Standard deviation divided by the square root of the sample size. Standard deviation is 15.8. So dividing that by the square root of 100. So we're looking at 15.8 divided by 10, which is 1.58 exactly. And there we go. That's all. That has been done. Okay, moving right along. Let's talk about what happens when we sample from a normal population. So, sorry, I need to put a little in-between action there. All right. So it's the case, guys, that if a population is normally distributed, and you have, so if we have normally distributed population, right, we can talk about that in terms of mean and standard deviation. And if we're sampling from that normal population, right, the sampling distribution of x bar is going to be normal as well, okay? Alright, so we got with mean, so it's going to share the same mean, and standard deviation. Is going to be, we're looking at the standard deviation of the sample mean right there. So now that we know these things, we can go ahead and do a problem. Let's do a problem. Okay. So, sorry, but sorry for anybody with peanut allergies, but we're going to talk about the 90 Peanuts Company. So the distribution of weights in these jars is approximately normal with a mean of 16.1 and a standard deviation of 0.15. Without doing any calculations, which outcome is more likely? Randomly selecting a single jar and finding that the contents weighs less than 16 ounces, or randomly selecting 10 jars and finding that the average weight is less than 16 ounces. So we select a single jar. Huh? I think about it. Yeah. I agree. I agree. Yes, the first one for the exact reason that you said. Yeah. So, and what you're saying is, so I'll give you the book answer. It's exactly what you're saying. Because averages are less variable than individual measurements, you would expect the sample mean in 10 jars to be closer, on average, to the true mean of 16.1 ounces. Thus, it's more likely that a single jar would be less than 16 ounces than for the average weight of 10 jars to be less. So there's going to be less variability in the sample mean than there would be in just one sample that you would take. All right. Let's get down to the nitty-gritty. Let's find the probability that a randomly selected jar contains less than 16 ounces of peanuts. All right. So first of all, let's get together all of our statistics that we need. All right, let's talk about the distribution. So we're sampling. Okay, sorry, I thought we were taking your sample. So we're just doing a normal calculation with this one, right? There's nothing to it. We'll have to, with our 10 randomly selected jars, then we're going to have to actually recalculate the standard deviation. So, so we're going to skip to C because B is like everything else that we've done before. But with this one, things are a little bit different. The mean of our sample means is the same as the mean of the population, which is going to be 16.1. I would like to know what the standard deviation is, but before I can do that, I need to check the 10% condition. So is it the case that my sample is So is this true? Let's find out. I'm going to say that there probably are more than 100 peanuts. Fantastic. So then we can go ahead and calculate our standard deviation then, which is going to be the standard deviation of the population divided by the square root of the sample size. So we're going to have 0.15 divided by the square root of 100, which is 0.15 divided by 10, which is why is my brain being here? I don't know why I chose 100. Thank you. Where did I get? I think I was thinking about the last problem. Sorry. Thanks. So square root of 10. So how would you get? I'm getting approximately 0.047. Okay, so now that we know that, what are we looking for? Yeah. So now what do we want to know? We want to know, what's probability? I need the problem here. Is less than, so we need to know the probability that x okay, so that's the same thing as the probability that z is less than or equal to 16.1 minus 16 over 0.0. Which is only oh, this is going to be extremely low. 1, 2, 8. It's been a little while since we went and got this from a z table. Been doing calculations with a calculator for a while. My goodness, thank you. I switched these for some reason. That's not fun. That makes this negative. Well, x minus mu to 3, so that makes that negative. Thank you. Wow. And then if I go to my z table and look for negative 2.128, 2.1, 2.1, 2. So 0.017. Zero. All right, cool. So now we've got our calculations. Let's go ahead and state our answer. Make sure all right. There it is. Done. Cool. Not too bad. I really like this notation the most, by the way. Just because it has more of a flow to it. I like lining up some equal signs. That's a nice flow when you do it like that. Huh? Okay. So this is really weird, right? We got a very strangely shaped population distribution. But if we start to sample from this population, it's super skewed, right? It's just really weird. But as we sample from this population, the distribution of the sample means looks more and more like a normal distribution the larger that our sample is, right? And that really drives us right into the central limit theorem, which tells us that if you draw a simple random sample of size n from any population with a mean, mu, and standard deviation, sigma, the central limit theorem, and we call it CLT, says that when n is large, the sampling distribution of the sample mean, x bar, is approximately normal. Kind of what we've been getting at the entire time we've been talking, right? It's really nice because it allows us to use normal calculations when we're looking at sample means. And that's it in a nutshell for this. You can kind of see what's going on. It's nice to look at a graphic of what happens in something that's definitely not normal, right? But we can use normal approximations if we take enough samples and look at the distribution of the sample means instead. All right. Here we go. All right, so last problem. Suppose that the mean number of texts entering a typical day by students at a particular high school follows a right skew distribution with a mean of 45 and a standard deviation of 35. We want to know how likely is it that a random sample of 50 students will have sent more than a total of 2,500 texts in one day. Okay. So first thing we need to do is get all our stuff for our distribution sorted out. So it doesn't look like this is actually a normal distribution, does it? It says it's skewed. Right. So then, okay. So what have we got? Our mean is x bar, right? And our standard deviation is actually s of x. All right. So, but what we're really looking for is we want to know what mu sub x is. It's going to be the same thing as the mean of our sample. And then we also need to know what the standard deviation is. Well, we need to check. our 10% condition, right? So, is it the case that little n is less than or equal to 1/10 of the units, or in other words, it's 10? So that's going to be 500. And we're looking at the high school, right? So there's probably, huh? Yeah, we're number of texts. There's got to be more than 500 texts sent during a day, right? I mean,
Isn't it an occasion? So this is like a certain instance. So we have 500 instances of text being sent.
not to a particular student.
Or a particular student.
By students, by all students. The number of texts sent during a typical day by all students. So that's got to be more than 500, right? Okay. Cool beans. All right. So, okay. Cool. So that is that. All right. So then we can take our standard deviation. So our new standard deviation, our sample standard deviation, is going to be 35 divided by square root of 50. No. This should be X bar. I had a feeling something was wrong. All right, I'll get out my handy dandy calculator. Where are we? All right, 35 divided by the square root of 50 is approximately 4.95. All right, so now we're able to make a shift, right? Now that we've said that that 10% condition is met, we can shift and say that we can represent this in terms of a normal distribution, right? So we can say that X bar is approximately normal. The distribution, by the way. I don't want to say X bar is approximately normal. It's the distribution of X bar that is approximately normal. And it would follow the distribution then. Okay, so now we can solve the problem. We want to know the probability that X bar is
Wouldn't it be opposite?
Yeah. At least. Okay, so that's going to look like we have our all we need is this information here. So that's going to look like this. So yeah, if we're looking at the normal curve, and this is our mean is 45. Then if we calculate this, right? Then I mean 2,500 is, you know, like somewhere maybe way over here, right? This area is virtually zero. It's so close to zero. So something's wrong, right? This calculation must not be the calculation that we need to make. So that's where my brain is going. There's something else going on here. Okay, so that probability is wrong because if our mean is 2,500, sorry, if we have 2,500 texts for 50 students, what we're really looking at is that the probability that the mean is 50, right? Because 50, because 2,500 divided by. So we're looking at the idea that the probability that if the mean is 50, we're looking at the probability that each student said 50 texts, right? In a way. Yeah? So this is going to give us a better calculation. Oh, weird. That's better. Is it whack? Alright, so now let's do this. So the probability x bar greater than 50. At this point, it's pretty easy to do, right? We can get a z value, x value, and then I'd say let's just use our handy-dandy calculator to save. So we'll get a value for this by doing norm CDF. We'll go lower, upper, my bad, lower, upper, this is 10 to the 99th we could use. Well, they use 1,000, but anyways, our calculator will do 10 to the 99. And then our mean, and then our standard deviation. That will give us 0.15. Cool. All right. There we go. That was a tricky one.
Look for the little trickiness.
Yes. That's our upper bound, right? Remember, so it has to be like as close to infinity as you could get, right? Essentially, if you could put infinity in there, it would be best because that data looks pretty good. Cool. All right. Done.